Welcome to section 1.3, which is rates of change and the behavior of graphs. So rates of change and the behavior of graphs. Okay, so definition. So let's let f of x be a given function, right? So remember, functions pass the vertical line test. So be a given function. Then the average rate of change, that's what we're defining, the average rate of change for f of x over the interval, and this interval is part of the domain, so closed at A to closed at B is given by and we'll call the average rate of change ARC. So that'll be f of B minus f of A all over B minus A. So that's the average rate of change. So let's consider something. So consider so I'm going to draw x and y coordinate axes. Give ourselves a lot of room in quadrant 1. So x and y, let's draw a function f of x. Oh, that's terrible. Let's make it a bit nicer. Something like so. Here's my function f of x. And let's look at a point A on the x-axis. So the corresponding value for y would be f at A. Now let's look at a point B on the x-axis. So the corresponding value for y on the graph at that point would be f at B, the value for y. So the interval I is between A and B. So this is the interval I that is between A and B. That's our A and B interval right there. So the average rate of change actually has to do with, let's use green. If I look at the line that goes through these 2 points, actually let me make it actually go through these 2 points. So we've got a line going through here. So this is called the secant line. Through points A, comma, f of A and B, comma, f of B. Okay, so we call that the secant line. Okay, now let's consider what is the distance here. So I claim that this distance is going to be largest y value, f of B, minus smallest y value, f of A. So the distance between these two is their difference. Similarly, the distance on the x-axis is going to be the difference between the larger value b and the smaller value a. So notice that the slope of the secant line, so what color should I use for slope? So the slope m of the secant line, which is green, is the rise over the run, right? So rise over run is what we use for slope, meaning change in y. So what color should I use? Change in y. Change in y over change in x. We rise vertically and run horizontally. So change in x. So the math notation for that is called delta, means change. So delta y, change in y, over delta x means change in x. Okay, so let's look at this. What is the slope? So from the first point here at a comma f of a to the second point here at b comma f of b, we rise the distance along the y-axis, then run the distance along the x-axis. So I claim that that's going to be, in the numerator, we will have f of b minus f of a for the change in y, whereas in the denominator, we will have the change in x, which is the distance I there, so it's b minus a. So that is i.e. So i.e. the average rate of change, the ARC, is equal to the slope, m, of the secant line. Okay, so that's what the average rate of change is, the slope of the secant line. Okay, so for example, let's actually evaluate the average rate of change. So let's let f of x be as pictured below, as pictured below. Let's find the average rate of change, the ARC, for f of x over the intervals let's do from -2 to 1 and from -1 to 1. Okay, so let me give you the graph. So x and y coordinate axes. X and y. Let's do 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 1, 2, 3. Okay, so the graph of my function, let's say it's a parabola with vertex at -1, -2. So 1, 2, 3, 4. So it looks something like so. A nice quadratic function. And I won't give you the formula for it now. I could, but it doesn't really matter. So f of x is this function right here. Okay, what the heck, I'll give it to you. So it would be x plus 1 quantity squared minus 2 if you cared, but it doesn't matter. So we'll get to that later. Let's consider the interval from -2 to 1. So that's from here to here on the x-axis. So that'll be from this point to this point. So I want to know what is the average rate of change between those 2 points. So I claim that the average rate of change on the interval from -2 to 1 will be f at 1 minus f at -2 all over 1 minus a -2. Okay, so let's see what we have here. What is the value of the function at 1? So it looks like the value of the function at 1, the y value is 2, from which I'm subtracting. What is the value of the function at -2? So it looks like the value of the function at -2, the value for y is -1. And in the denominator, we have that 2 negatives make a positive, so this is 1 plus 2. So what do we get? We get 2 plus 1 over 1 plus 2. Anything divided by himself is just going to be 1. Now, is it true that the slope of this line is 1? This purple line here, is that 1? If I rise 1, run 1, rise 1, run 1, rise 1, run 1, yes. Looks like the slope of that purple secant line is indeed 1. So now let's look at the average rate of change between -1 and 1. So now the average rate of change for the function between -1 and 1, well, now between here and here. So that corresponds to this point here and that same other point there. So I'm looking now at that green secant line. So I claim that that will be f at 1 minus f at -1 all over 1 minus a -1. So once again, let's see what we have here. Let's look at the value for f at 1. Well, it's still the same, right? It's still this 2. The y value is still 2. Minus, let's look now at the value for f at, what color should I use? Orange. So let's look at the value for the function when x is -1. It looks like it's -2. And in the denominator, we have 1 minus a negative, so that becomes 1 plus 1. So what do we have in the numerator? 2 plus 2 is 4. Over 2 is 2 over 1. So is it true that my green secant line, rise 2, run 1, rise 2, run 1? Yes, it's true that the slope of the secant line is indeed 2 on the graph between -1 and 1. Okay, so hopefully that's making sense. Now let's do it analytically. Let's see, do I have room? I don't know if I have room to add another one. So what I'm going to do is I'm just going to move this down a bit so it's not skipping that much space. There we go. Okay, so let's go to the next page then. So example. So find the average rate of change. Find the average rate of change algebraically. Average rate of change on the interval interval. Remember, these are x values, the interval given, and the interval indicated, or intervals rather, indicated in the following. So number 1, subscript number 1, let's say we have that f of x is given as 1 over x plus 5, say. X plus 5, and let's consider the interval I as being between -4 and 0. Okay, so we know that the average rate of change is going to be equal to f of b minus f of a all over b minus a. So if this is a, that'll be -4 for a. And this is b, that'll be 0 for b. So it's always second guy minus first guy. Okay, so what do we have then? So it looks like we have, I guess I'll need a bit more room. 1 divided by 0 plus 5. That's f at b, from which we're subtracting. 1 divided by a -4 plus 5. And we're dividing all of that by minus a -4, which becomes +4 in the denominator. Okay, so what do we have? Looks like we have 1/5, from which we're subtracting 1 and dividing that by 4. So how many fifths is 1? Well, all whole numbers are divided by 1. So 1 over 1, in order to get 5 in the denominator, I'd have to multiply by 5 top and bottom. So 5/5 is the same as 1. So it looks like we have 4/5 divided by 4 as a whole number. So 4 as a whole number is really 4 over 1. So we can invert and multiply when we divide two fractions. This will be 4/5 times the reciprocal 1/4. So the 4's reduce, and I'm left with an average rate of change, or slope of the secant line, as 1/5. Okay, so that's algebraically. Let's do another one. Subscript number 2. Let's say we have that f of x is equal to 2x cubed plus 1, and the interval I on which I want to evaluate the average rate of change will be for values of x between -1 and +2. Okay, so the average rate of change is going to be f of b minus f of a all over b minus a. So in our case, the second coordinate on the interval is 2. So let me actually do that one first. So this is my b, so f of 2. And my first coordinate is, what color should I use? Yellow. Minus f of a -1, that's my a, all divided by 2 minus a -1. Okay, so what do we get here? If I plug in, I get 2 times 2 cubed plus 1, from which I'm subtracting 2 times a negative 1 cubed plus 1, and dividing all of that by 2 minus a negative, or 2 plus 1 is 3. So what do we have? So in the first parenthetical, we have 16 plus 1 is 17. Minus, in the second parenthetical, we have negative 1 times 2 is negative 2 plus 1 is negative 1. So this will be minus a negative 1 all over 3. So 17 minus a negative 1 is 18 divided by 3. So that becomes 6. So the average rate of change for that function on the given interval is 6. So that's the slope of the secant line. Okay, so the last one for this example. Let's say we have that f of x is the square root of 5x minus 3. And we want the interval, the average rate of change on the interval from 4/5 to 19/5. It's terrible, 19/5. Okay, so the average rate of change is going to be f of b minus f of a all over b minus a. Okay, so that's f of the second coordinate minus f of the first coordinate all over second coordinate minus first. So the second coordinate is 19/5, and the first coordinate is 4/5. Okay, so what are we going to have here? We're going to have the square root of 5 times 19/5, from which I'm subtracting 3 underneath the first radical. Then we're going to subtract from that. Actually, I don't like those extra. I don't really need those because they're under a radical. Okay, let me make this a bit better. So now I'm going to subtract the next radical, which will be 5 times a, which is 4/5, from which I'm subtracting 3 underneath that radical. And I'm dividing all of this by 19 minus 4 is 15/5. I'll simplify that in a moment. So what I get underneath the first radical is the 5's reduce. Let me show that. So the 5's reduce, and I'm left with the square root of 19. Actually, let me color code. 19 minus 3 minus the square root of, once again, the 5's reduce, and I'm left with the square root of 4 minus 3. And this negative should have been in blue. And that's all divided by, well, now 5 goes into 15 3 times. Okay, so what do I have? 19 minus 3 is 16. So I have root 16 minus 4 minus 3 is 1. The square root of 1 all over 3. Okay, so root 16 is 4 minus the square root of 1. Positive square root of 1 is 1 all over 3. So 3 divided by 3 is 1. So that is the average rate of change for that function on that specific interval. So now let's kick it up a notch, shall we? So for example, so determine the regions, how do I want to say this? Let's do it this way. So find the average rate of change find the average rate of change, the ARC, average rate of change on the interval. Let's do the interval from x to x plus h for the following. So number 1, let's say the first function is 1 over x minus 9. Okay, so I know that the average rate of change is going to be f of b minus f of a. So my a and my b, let me color code them. This is my a, and this is my b. So let's do f of my b, which is x plus h, minus f of my a, which is just x, all over b, which is x plus h in this case, minus x. Okay, so what do we have here? So in the numerator, let's look at the first guy. It's going to be 1 over x plus h. Wherever there's an x, I replace it with the whole input x plus h minus 9, from which I'm subtracting 1 over simply x minus 9. It's the same function, not really doing anything. All over, that's just in the numerator. We'll notice that x minus x goes away. So all that's left in the denominator is h. Okay, this is what's known as a complex fraction. So in order to make this without fractions within fractions, what we want to do is multiply top and bottom by the LCD. That is, we want to multiply the numerator by x plus h minus 9 and x minus 9. Then we want to multiply the denominator by the same thing. So notice I'm really just multiplying by 1, because anything divided by itself is 1. So I'm not changing anything. So now if I distribute to each term in the numerator, what do we have? Well, let me initially be explicit, show you what I'm doing. So 1 over x plus h minus 9. We're going to distribute that whole ugly orange guy here. So I'm going to distribute x plus h minus 9 and x minus 9 to this first term. Then we're going to subtract 1 over x minus 9, where x is in purple this time. And we're also going to distribute that orange guy to this term. So x plus h minus 9 times x minus 9 minus 9. Okay, now I'm going to also distribute orange, big ugly guy, in the denominator. So now I'll have h times orange guy, which is x plus h minus 9 times x minus 9. And you might say, why have you done this? Well, x plus h minus 9 reduces here, and x minus 9 reduces here. So what I'm left with in the numerator now is simply 1 times the quantity x minus 9 in for the first term, from which I'm subtracting 1 times the quantity x plus h minus 9 in the second term. All over, there's nothing I can do to simplify the denominator, so I just leave it as h times the quantity x plus h minus 9 times x minus 9. Notice now I no longer have fractions within fractions. So let me go ahead and distribute this negative 1 inside here. So each term will now be negative. So what I'll have in the numerator now will be x minus 9. And then distributing the negative 1, we'll have negative x, negative h, and positive 9 all over h times the quantity x plus h minus 9 times the quantity x minus 9. But notice now that x minus x goes away, that negative 9 and positive 9 go away. So what am I left with? I'm left with a negative h divided by a positive h times the quantity x plus h minus 9 times x minus 9. And if you noticed, we can reduce that h, and that'll be the last thing we can do. We can reduce h over h to 1 over 1. So when all is said and done, this can be simplified as negative 1 divided by just the orange guy. The h has reduced. Quantity x plus h minus 9 times the quantity x minus 9. Okay, that builds character, doesn't it? Let's see. Okay, good. Let's do another one. So subscript number 2, let's do the same thing for f of x is equal to 2x cubed minus 5. So I want to find the average rate of change, which I know is going to be f of b minus f of a all over b minus a. So for us, that's going to be f of, what color did I use? Did I use pink first? Yeah. X plus h minus f of x all over x plus h minus x. Okay, so what do we have then? Looks like we'll have 2 times the quantity x plus h cubed minus 5, from which we're subtracting 2 times the quantity x cubed minus 5 all over. Notice that the x's, actually let me do this in yellow, x minus x reduces, and I'm left simply with an h in the denominator. So now we need to do 2 things. We need to distribute this negative, and we need to expand the trinomial x plus h cubed. So this becomes 2 times the quantity. Using Pascal's triangle, this is x cubed plus 3x squared h plus 3xh squared plus h cubed. Oh, and parentheses, sorry. Minus 5, and then I'm distributing the negative. This will now be minus 2x cubed minus a negative or plus 5 all over h And we see right away that -5 and +5 can reduce. So let's go ahead and distribute the 2 inside here, etc. Okay. So what do we get? We get 2 x cubed plus 6 x squared h plus 6 xh squared plus 2 h cubed, from which we're subtracting 2x cubed and dividing all of that by h. Okay, so let's notice that 2x cubed minus 2x cubed reduces. So we are left with 6 x squared h plus 6hx squared, 6xh squared plus 2h cubed, all divided by h. So notice that there's an h in every single term. So I can factor an h out of the numerator. So when I do that, when I factor an h from the numerator, what remains from the first term is just a 6x squared. From the second term, a 6x and 1h. And from the third term, a 2h squared. This is all divided by h. So the h's now reduce. And when all is said and done, this simplifies to simply 6x squared plus 6xh plus 2h squared. Ah, that was fun now, wasn't it? Okay, let's do one more of these for good measure. Third time's a charm. Okay, so we have that f of x is equal to the square root of x minus 1 on the same interval from x to x plus h. So the average rate of change is going to be f of b minus f of a all over b minus a. But for us, the b is x plus h. Oops, wrong color. So f of x plus h minus f of x all over x plus h minus x. So this gives us the square root of x plus h minus 1 for the first guy minus the square root of just x minus 1, all divided by, well, notice that x minus x goes away, so I'm just dividing this by h. So what I'm going to do is I'm going to rationalize the numerator, meaning I'm going to multiply by the conjugate of the numerator, top and bottom. So I'll multiply by root x plus h minus 1 plus the square root of x minus 1. So what that's going to do is force the difference of squares. So remember, I can't change anything, so I need to multiply by 1. So whatever I do in the numerator, I do in the denominator. So now let's distribute. So this will give us the square root of x plus h minus 1 the whole quantity squared minus the square root of x minus 1, the whole quantity squared, because I have the difference of squares in the numerator, all divided by h times, in parentheses, the square root of x plus h minus 1 plus the square root of x minus 1. And this step is because if I have a plus b times a minus b, that's a squared minus b squared. That's a difference of squares. So that's what I've employed in the numerator. That's why we multiply by the conjugate, to force the difference of squares. So now in the numerator what we get is x plus h minus 1, from which we're subtracting x minus 1. So we're going to need to distribute that negative. All divided by, wrong color, h times the quantity, root x plus h minus 1, plus the square root of x minus 1. Okay, so now let's go ahead and distribute this negative inside this parenthetical. So what do we get? We get x plus h minus 1. Then we get minus x and minus a negative, or plus 1, all over h times the quantity, the square root of x plus h minus 1, to which we're adding the square root of x minus 1, end parentheses. Okay, so notice that x minus x goes away, and that negative 1, positive 1, sum to 0. So I'm left with h in the numerator divided by h times the quantity, it's a terrible h times the quantity, square root of x plus h minus 1, plus the square root of x minus 1. And now we see that the h's reduce, giving us 1 over 1. So this will be 1 divided by that orange monstrosity, square root of x plus h minus 1, to which we're adding the square root of x minus 1. And there we are. Holy free holy. That was a lot, wasn't it? But it's fun. It's an exercise in concentration. Okay. So let's consider x and y coordinate axes. And let's have a nice sinuous graph that looks something like so. Sinusoidal in a sense. So here's my function f of x. So notice that at this point here, let's call this A, looks like we've hit a trough of sorts, which we can call a minimum, if you will. And at this point, maybe about here, looks like we've hit a peak of sorts. No, let's call this B, which looks like it's locally a little maximum. And once again, looks like about here. Let's call this point about C. Looks like I've hit another, what looks like a minimum locally. Okay. So we'll get to the mins and maxes at a moment. But what I'd like to note that in reading direction from left to right, that I'm going downhill from the left until I get to A. And once again, I'm going downhill between B and C. So in reading direction, from left to right in English, left to right in English, the graph tends, or trends, not tends, trends would be a better word, trends downhill, on the intervals from minus infinity to all the way to the left to A. But at A, we'll have to consider what happens at A. And then once again, so union between B and C. Okay. What other color should I use here? Should I use green? Maybe a gold. Gold is not different enough. Let's use, okay, maybe a green. Teal is good. No, it's not. I just don't know what color. So now let's look at between A and B. So between A and B, reading from left to right, I'm going uphill. And from C all the way to the right, to the positive infinite, I'm once again going uphill. So the graph trends uphill on the intervals rather. What are the intervals? Between A and B. So between A and B, but not at either, and so union. From C towards all the way to the right, positive infinite. So let's note what happens at A, B, and C. So note. So there's a localized minimums at x equals to A and x equals to B. Sorry, x equals to C. Right, locally, if I look at just a region, I don't know, maybe a region of radius delta on either side. So if I'm within delta on either side of these values of x, do you agree that in that region, that little region here, that C is a minimum? Did I? Yeah, I put minimum. Just want to make sure I wrote the right word. So that the value is minimized on this little interval. And we had a localized maximum, right? So localized max. Localized maximum at x equals to B. Actually, technically, the value of the function is maximized, so this is my maximum. So that means that if I just look at a little region around B, say a delta on either side, that if I look at this region, just this region, that the largest value for the function is at B. Okay, so let's define some of this stuff. What do I have? I have regions of going downhill. I have regions of going uphill. I have localized minimums and localized maximums. Okay, so that's what we're considering here. So definition. Let's do this in a darker blue. So definition. So the graph of f of x, the graph of f of x is, number one, increasing. So that's our first definition, increasing on an interval I, an interval. Remember, this interval I is always values of x. If for all AB elements of the interval such that B is larger than A, then this means that f of B is less than f of A if we're increasing. So let's see, what does that mean? So if I'm going uphill, sorry, increasing, no, what do I want? I want this to be greater than, what am I saying? Increasing in rating. Okay, got to figure this out. So I've got a perfect picture of A and B here that satisfy that B is larger than A, which means that f of B is greater than f of A. And do you agree I'm going uphill in this region? So therefore my y values for greater values of x are also correspond. Okay, got that right. Got to make sure. So this is very formal. What I want you to understand is that in reading direction, you're going uphill if it's increasing. So the analogous definition for decreasing if you're going downhill in reading direction, right? So decreasing on an interval I. On an interval I. If for all A and B on that interval such that B is larger than A. So now we want that the y values are decreasing. So now we want that f of B is less than f of A. So if we look at this part where we're going downhill, my y values start off positive and get a little bit more negative because my y values are decreasing as my x values are increasing. Pardon me. Oh my goodness, this smoke is going to kill me. So definition. Okay, so the graph of f of x has, so we did increasing and decreasing, which is really just going uphill or downhill. So the graph of f of x has, so what else did I plot up there that we need to address? That's local minimums and local maximums, right? So has A, so definition number one, let's call it local maximum, at f of A if there exists a radius delta greater than 0 such that f of x is less than f of A for all x on that interval. So a minus delta to a plus delta. So this is basically what I plotted. So do you agree I've got a local maximum here, which means that all of the values for y, except for the value at, will be less than the value at b. So less than the value at my max. So if I'm within a radius delta of the maximum, my values for y are all less, except at that, right? So we have to indicate that. I guess it should be so for all, in particular, x is not equal to a, right? So for all values for which x is not equal to a, then it's less than. That should be evident, but you get the idea. So local minimum will be the same way. I want that all values of f now be greater than. So at f of a, if there exists a positive radius delta, such that f of x, the y value, is now greater than the value at a for all values of x within a delta radius of a, so a minus delta to a plus delta, where x is not equal to a. So what does that mean? That means if I go a plus delta, a minus delta, all values of y are greater than the value at a. Notice a is the minimum, right? So if I'm looking at the x values within a delta radius of a, all values of y will be larger than my minimum. Okay, that's a very formalized definition. So let's note. Okay, so these are collectively termed. Local extrema. Sometimes you'll hear them be termed local extremes, but local extrema is fine. Okay, so for example, do I have enough room to put an example here? Maybe I should go to the next page. Yeah, let's go to the next page. Okay, so for example, so determine the regions on which, do you know what? Before I do this, let me just put an extra note up here. So note. At the local extrema, the graph of f of x is neither increasing nor decreasing. So neither increasing nor decreasing. Hence, intervals of increasing/decreasing are always open. Meaning we don't have square brackets, we only have open brackets. Okay, so determine the regions at which or on which. So determine the regions on which f of x is increasing, decreasing, and where it has any local extrema. And how about the points at which? The points at which it has any local extrema. Okay, so I'm going to give you a graph. So x and y coordinate axes. One, two, three, four. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So the graph is point here, a point here, point here. Terrible graph. Something like that. Okay, so this is my f of x. Okay, so let's look at increasing. So increasing, that would be going uphill in reading direction. Well, the only part that it's going uphill, oops, see if I can do this, seems to be here. So that's between -2 and +2 on the x. So it's increasing between -2 and 2. What about decreasing? So going downhill in reading direction. Looks like it's going downhill here, and it's also going downhill here. So it looks like it starts all the way to the left, which is negative infinite, comes to -2, union, then it starts again at 2 and goes all the way off to the positive infinite. So that's where it's going downhill in reading direction. Now let's see, do we have a minimum? Let me move these over a bit. So do I have a minimum or local minimum? Let me put local. Local min. Local minimum. Well, this point looks like it's a minimum locally. I can find a little region about which all the values of y are larger. So that would be at -2, comma, what's that, -3? -3. Now, are there a local maximum? Now, what color should I use for that? Local max? Well, it looks like this point is locally a little maximum. So that would be at the point 2, comma, what is that, 3 on the y? Okay, so there we are. Okay. So let's look again at our standard functions. And we're going to do this analysis for all of the standard functions. So maybe I can move this over to the right a bit. That seems a bit too left adjusted for my taste. Okay, there we go. That's better. Okay, so let's look at standard functions. The ones we've gone over before. But now we're going to analyze where they're increasing and decreasing and whatnot. Okay, so let's say we have f of x is some real number c. So that's the constant function, right? So a constant function . is a horizontal line. So here's C, and it is the horizontal line through C. So do you agree that neither increasing nor decreasing? So neither increasing or decreasing, and no extrema. Okay, let's look at the identity function, which is f of x is equal to x. So that's the main diagonal. So therefore that is increasing, always from left to right, it's always going uphill. Increasing on the interval all the way to the left to all the way to the right. And no extrema. Because it will neither hit its minimum nor its maximum, because it goes on forever. Let's say we have f of x is equal to x squared, which is our quadratic function. Terrible quadratic graph. Let me see if I can draw that a bit better. Just a bit, that would be nice. Okay, well, yeah, I tried. Okay, so we can see that this is decreasing until I get to 0. So all the way to the left, it's going downhill till x is 0. It's increasing to the right of 0, meaning going uphill when x is beyond 0. And it looks like there's a local min at 0, 0. Okay. Let's do the cubic. So f of x is x cubed. So that's actually a nice S-shaped graph. Vertically inclined. Okay, so this looks like it's always going uphill, so increasing on all real numbers, so from all the way to the left to all the way to the right, and no extrema. It will neither hit its minimum nor its maximum. What color should I do now? Let's do purple again. Different color purple. Let's do that color purple. Let's do the reciprocal function, 1 over x. Okay, so the reciprocal function I can move that up a bit. So 1 over x looks something like so. Not drawn very well. I wish I could draw a bit better. That would be nice. Okay, so this is actually from left to right. It's always decreasing except at 0. And the reason it's not decreasing at 0 is because we've got something on the graph at 0. For x equals to 0, we have a vertical asymptote. And thou shalt not cross a vertical asymptote, which means it's not in the domain. So therefore, it would be impossible to either be increasing or decreasing on a vertical asymptote. Okay, the last one I'd like to do, unfortunately, this will take me to the next page, but that's okay. Let's do f of x is equal to 1 over x squared, the reciprocal squared. And I'll show you how this differs from the one above. It differs in that this negative part flips and is now positive. Oh my goodness. Come on. Okay, so notice that this is going uphill now, so it's increasing until I get to 0. So all the way to the left to 0. But then it's decreasing, going downhill from 0 all the way to the right. But we still don't have anything at 0 because this is a vertical asymptote. This is where we shall not divide by 0. Okay, so let's do the roots, shall we? Maybe the cube root of x, which is kind of similar to the cube. Only this time, instead of being vertically inclined, it's horizontally inclined. So the cubed root function looks something like so. So it's always going uphill in reading direction, so it's increasing everywhere. From all the way to the left to all the way to the right, so minus infinity to infinity. But there's no extrema. Okay. Let's look at the square root. So f of x is equal to just the square root of x. So half a parabola opening to the right. This is actually increasing on its entire domain. It's increasing, but its domain only includes those things to the right. And it looks like there's a minimum value. The minimum value will be at 0, 0, because all other values will be larger. So that's interesting. Okay, one left for good measure. Let's do f of x is equal to the absolute value of x. And we know that that looks like a little v. So let's go ahead and plot that. X and y. Okay, so this is clearly decreasing all the way to the left to 0. Then it's increasing from 0 all the way to the right. Increasing from 0 all the way to the right. And it looks like there is a minimum at 0, 0. So local min. Well, actually, we'll just put min at 0, 0. So hopefully this is making sense so far. Okay, and I keep on swapping up local versus just min. Why am I doing that? And I'll show you now why I do that. So definition. Okay, so the graph of f of x. So the graph of f of x has an, number 1, absolute maximum. Absolute maximum. So this will differ from local maximums. So an absolute maximum at x equal to a if f of x is less than f of a for all x is not equal to a in the entire domain of the function. Meaning there is no larger value for y. It has an absolute minimum. Absolute minimum. Absolute minimum at x equal to a if there's no smaller value. So if f of x is larger than f of a, so every other value of y is larger for all x not equal to a in the domain of the function. So note, these are collectively called the global extrema. So note, these are collectively called the global or absolute extrema. Okay, so for example, so determine the intervals on which the following, let's do increasing, decreasing, and list any global extrema. Okay, so determine the intervals on which f of x is increasing and or decreasing where it has any local or global extrema, and where it has, and where it has, and where it has any local or global extrema. Okay, so now I need to draw this for you. So x and y coordinate axes, I want to go up to 1, 2, 3, 1, 2, 3, 4. Hopefully I've got enough room. Let's see if I do. 1, 2. So I want to go up to 3. 1, 2, 3. 1, 2, 3, 4. So where should I put my, well, I guess I'll put it here. So x and y. Let's go out to 2, 2, 3. 1, 2, 3. Okay, so now I've got a function that looks like so. Oh, guess I could have gone down farther. Oh well. Okay. Oh, terrible. Okay, why is it so difficult for me to draw these things? I don't understand. How does that look? I don't like the way it looks. And now I'm getting my chords all mixed up. Let's see. That last bit doesn't look that great. Let's see. Okay. I suppose that'll have to do. So this is f of x. Do you know what I could do? I could bring this down a bit, make it not so cramped. There we go. Okay, so here's my f of x. And let's answer all the questions. So let's do increasing. So going uphill looks like from in reading direction, These are the regions on which I'm increasing. So that's to -2 to 2. Okay, so it looks like to the left of -2 all the way to -2. Then once again, for values of x to the right of 2. So decreasing, looks like I'm going downhill between, for values of x, between -2 and 2. So this looks like, since this is an arrow, so let me make sure I understand this is an arrow and this is an arrow. Actually, no. Do you know what? Let's not make it an arrow. Let's make it something else. Let's make this a point so that we can see. Let's go down here. Let's have it stop. In which case, if I do that, I'm increasing, what would that be? -4 on the x-axis there. Right here. Yeah, it looks like -4. So I'd be increasing from -4 to -2. But what I can do now is if I look at a minimum value, so this is going to be a global, because there's no smaller value now for y. So this is the smallest value for y, and it's at -2. So the global min is going to be at -4 for x and -2 for y. So that's my global minimum point. But I have a local minimum here. Not the local minimum, so local min. Meaning there is another smaller point, but it's to the left. Locally, I minimize, let's say that's -1 at 2, -1. And then do I have a maximum? Yes, I have a local max. And the reason it's local is because of this arrow here. So I have a local maximum at the point -2, 1, 2, 3. 3. Okay, so these are local versus global. And let me make sure we understand this. Let me put a big arrow on this. Arrow. This is going up forever. Okay. So hopefully this makes sense. Remember increasing in reading direction or decreasing in reading direction. Okay, anyways, I did it. I put it on the same page. Let me just push this a little bit to the right because I do have the room. That looks a bit better. Make this axis something like so. Okay, so there we are. And I will see you guys in the next video.